so this is our video for lesson 2.3, understanding the derivative. There will be something here you're going to want to have your calculator for, so just if you'll grab your calculator, you can pause right now, but just go ahead and turn it on and get it on and on a graphing page, so when we need it here in a minute, you'll be able to graph with me. So basically what we're going to talk about is how we can kind of estimate the derivative at a specific point, because very often that's what we're interested in. We're interested in just a very small change, and we want to know how does that affect things, and we call that a linear approximation. Well, we've already seen, because you drew some tangent lines next to some curves, that the tangent line look very close to the point of tangency. The curve and the tangent line are very, very, very close to the values. And so if we zoom in repeatedly really close to that, you'll look and see that the function actually looks to be linear. So if we get small enough, close enough to the point of tangency, it's really, you can't even tell the difference between the tangent line and the function itself. They're so close to the same. And so sometimes you'll be told to look at the local linearity. Sometimes you'll be told to do a linear approximation. Sometimes we'll say use the tangent line to approximate the derivative or the function value, things like that. And that's because of this feature. So what you need to do, and I'm actually going to do this on the calculator and not just show you those two graphs. So if you'll take your calculator and, oops, I hit the right thing. So I want you to graph sine x. So again, be on a graph page, so just hit pause if you need to. And you're just going to graph sine x and hit enter, and you're going to see that graph. Do not use the scratch pad. I know those things say scratch pad, but I really rather you not ever use the scratch pad. So just do this on a document. And then what we're going to do is we're going to zoom in really close to the origin. Now, zoom in and zoom out are not really something that I would really suggest you use, except in a case like this, where you're literally zooming in at a very specific place. And so you go to Menu, Window Zoom, and you have number 3, Zoom In. And they ask you for the center. So you're going to click with your touchpad, get to the center. So up here it's a little different. I'm not scrolling over there. You're going to scroll over, and then you just keep hitting the center, keep hitting the center, keep hitting the center. So if I zoom in, and then I'm going to hit escape, so my cursor's not doing that anymore. So you can see that if we zoom in like that, that definitely looks like a line. Okay, so if we get really close, then around 0, this function will look very much like the tangent line that we could draw there. And if you look carefully at it, it certainly looks like the slope appears to be 1. Okay, so if we wanted to estimate the slope there, so that's what it's going to tell you to do, is estimate the slope by looking at that zoomed in part, and we would definitely find that the slope appears to be 1. Now, of course, just by looking at it, we can't tell. It could be 0.99, you know, it could be 1.01. We don't really know, but it looks roughly equal to 1. And then we're going to find how to do that derivative algebraically or with calculus, so we'll be able to get that exact answer. So what that would tell us is, what that would say is that the slope of the tangent line at x equals 0 is 1 on the graph y equals sine x. So that's what we've found by estimating. Now we're estimating it, but if that was true, then we would say the slope of the tangent line at the point x equals 0 on this graph, we believe that that's 1. So if I wanted to write an equation of the tangent line for the graph of sine x at x equals 0, well, I would need to find the point. Of course, the point is 0, 0. So I would do y minus 0 equals the slope, which we know is 1 times x minus 0, or obviously simply y equals x. So the tangent line at 0 appears to be y equals x. All right. So now here you need to use a straight edge. So if you want to grab a ruler out of your protractor out of your packet, you can grab your protractor out to use your straight edge. I'm going to actually use the ruler tool here, and I'm going to draw tangent lines. So basically you're going to use a straight edge, and you're going to move it, and you're going to lay it along the points here. And I'm going to start with C just because that's the direction I happen to move it. So I have to change this a bit. So I got to slant it and then move it over. And so you're just trying to get it to be as perfect as you can get, where it's just tangent to that point. And then you're going to draw. So I would suggest drawing with, you know, a different color, like use your colored pencils. And I'm just going to draw, and there's my estimate for my tangent line there at that point. Okay, and I want to draw it pretty good because we're going to estimate the slopes too. So I'm going to do that for each of these. So you can just let this video run while I'm drawing mine, you're drawing yours, and then just look back at it in a minute and see if you kind of got the same things. So it'll be quiet here for a minute. I'm going to draw your drawing. So you take your straight edge and you draw what you think. And then again, you can just kind of look up here, look back at the video. So let's just do it for A here. So we'll do B in a second. Let's talk about A. So what we want to do is we want to estimate all the different slopes for question A. So let's start with the part at A. So I'm going to write slope with an A below it, a capital A, because they named that point A. So again, you're trying to communicate to people, what am I estimating? So I'm actually going to put approximately, because I'm not going to have an exact answer here, but I'm going to look for some points that it goes through. So it appears it obviously goes through this point. Let me use a different color. It obviously goes through this point because that's where we started. So that point is -5, -5. And I really just care about the y values. And then it appears to go through really close to the point for me where I drew it. So again, just the best I can. It appears to go through this point right here. So that would be a rise of 1, 2, 3, 4, and a run of 1. So for me, I'm going to get a slope of about 4. Now you might get something different because you're going to look. I mean, I can see how I could have turned that line just a smidge, and I would have probably said it was 5. Actually, I don't know if that is a good point right there, because that point would be to the side a little bit. So I'm going to take that piece off. It actually looks closer to this point. So I'm going to actually call that 5. Now, when we're estimating, we're going to estimate them pretty, you know, pretty liberally here. Now, for the slope of B, I actually don't have to estimate that. I can tell you that is 0 because that is clearly a horizontal line. And then for the slope here at C, it looks to me, if I go from that point that we started with, it looks like I'm going to go right through here. So it looks like a slope of -2. Okay, so those are my estimates for slopes. And I do want to change that to a squiggly equal. So when you're saying approximately, it's better to write that. All right, so that's what I'm estimating those slopes to be. So let's look at B. Now for B, I don't really need to draw anything because if I drew the tangent line, I would be on the line. So I mean, I can sort of decide, well, hey, this would be the tangent line here. Okay, and then this would be the tangent line through C, would be right through the exact line itself. That would be the tangent line there. And the one at B does not exist. Now let's look carefully at why that does not exist. The slope does not exist there because your tangent lines there, you clearly see there's two tangent lines coming in and they're different. So, and you could argue that you could put almost any kind of a tangent line there and you're definitely not going to get that to exist. So you've got to have the tangent lines, the slopes have to be the same from both sides. Just because think about the definition, it's a limit. So the limits are not the same from both sides, so the tangent line does not exist there at B. And the slope at this A, this point A is approximately, if we look at some points that it goes through, it looks like we just go up 1 or up 2 and left 1, so that makes -2. And the slope at C is, we go up 2 and right 1, so the slope at C is 2. And those are exact because those are actually on those points. Okay, so let's look at C and do the same thing. So you're going to take your protractor again. Again, you can pause the video or you can just, I'm going to do it at the same time. So you go ahead and draw yours while I'm drawing mine. And just draw them again. Line it up the best you can so you feel like it's only touching at that point. Yours should be a little quicker than mine. It's a little harder to move this ruler around. Looks pretty good. Again, they're not going to be perfect. It's okay. And then again, if we were trying to do a tangent line at B, this again does not exist because there is no way for me to have a tangent line that's the same. And the way I could actually look at that is, this one's even different in a different way. Like if I kept moving tangent lines closer and closer, and I just kept moving my ruler and I kept getting tangent lines closer and closer and closer to that point, you can see that pretty soon my line would be straight up and down, which would have an undefined slope. And so we say that the derivative actually does not exist there. We don't have one. So it appears to me, if I look at these points, it appears to me to go up 1 and left 2. So this slope at A appears to be -1/2, and the slope at C appears to be +1/2. Again, just check yours. All right, so let's do the last thing here. So if I look here at D and I were to draw these, again, let's take my tangent, my ruler, and just keep going and keep moving it closer and closer and closer to that point. Like if I was just going to keep trying to draw tangent lines over and over and over again, as I got closer and closer to this point, I'm going to end up until I very much would just have to have it straight up and down. So if we think about little tangent lines there, like if we were just to keep drawing them, we would just keep getting steeper and steeper and steeper. And same thing would happen coming from this side. And so you would end up with a line that is vertical. So that means the slope at this point A does not exist. And remember, don't put equals does not exist. We can't do that. Okay. So now let's answer some questions about what we found. So the position of it has to do with the concavity and tells us where the tangent line ends. So on question A here says, when the curve is concave up, where does the tangent line lie? So let's talk about these graphs and see where we have one that's concave up. And the only one we have that shows concave up would be on D here. If I were to draw a tangent line anywhere on this concave up part, so concave up means like a right side up bowl. The tangent lines are going to be underneath no matter what. And anytime I have concave down, like on part A here, you can see my tangent lines. No matter where I draw any tangent lines, this graph is concave down. Concave down means, again, like a upside down bowl. Your tangent lines are always going to be over the graph, okay? So those are two things that are important. When concave up, the tangent line lies below the graph. And this is important because you're going to have a lot of questions that are going to ask you, about that. So it's really important to start to get this connection. When the curve was concave down, like an upside down bowl, the tangent line lies always above the graph. Okay? And then at a turning point, which means a max or a min, well, where was the tangent line? Well, the tangent line was just horizontal there. But like if you look at point B here on A, you're going to have a horizontal tangent line at that point. So the tangent is 0 or horizontal. So the value is 0, the slope is 0, or you get a horizontal line is another way to look at it. So D, at a point of inflection, that's where the concavity changes. So let's look at question D here, where the concavity changes. So here you have concave up, and then right at this moment, you sort of switch, and now you have concave down, okay? So at this point of inflection, that's what we call that, the place where it changes, you're going to have a vertical. The tangent is going to be vertical, or it could possibly be 0. And I don't know if we have a graph where we're going to see that. None of these graphs are going to show that. But it could also be 0, but generally it's going to be vertical. But we can put vertical or 0 at a sharp corner or cusp. So where we had these sharp corners, like on part C here for B, that's what we call a cusp. That's where curvy things come in and make a point. And on B, part B, point B, we have what we call a sharp corner. When segments come in, we call it a corner. And both of those places, you will have the tangent line. The tangent does not exist there. So if you have a corner or a cusp, the tangent does not exist. And then at a point on a linear function, the tangent is the same slope as the line. I kind of usually say the tangent line is the line. So it's the same slope, same equation, all that. All right, so let's talk about algebraically how we can deal with this. Concept of estimating the derivative at a point. So we're going to take the function square root of x, and we should know what that function looks like. So the slope of this function at any given value is represented by f prime of x equals 1 over 2 square root of x. So they're telling you the answer for this slope. Okay? So they're going to tell you that. We're not going to find it. We're just going to give you the equation that gives you that answer. Okay? And I'm not sure if this matches your notes. I think it's going to be a little bit different possibly on your notes, but because it tells you to use the difference quotient, but we're not going to do that because we're going to go ahead and be given the formula. So A is just a little different. We're not going to use the difference quotient. We're going to just find the slope. Well, to find the slope at x equals 9, f prime is the slope. So f prime of 9 is going to give me the slope at 9. So f prime of 9 equals 1 over 2 times the square root of 9. And remember, this is the one and only time I let you work horizontally. One step here, one number, that's it. 1 over 2 times 3, which is 1/6. So we know that the slope at x equals 9 is 1/6 because f prime of 9 is 1/6. Then it says write an equation for the local linearization of f near x equals 9. So don't freak out about that. Okay, so the local linearization, your mind needs to think it says linear. The types of lines that we work with in calculus are tangent lines. So if somebody says write an equation for the local linearization, it's the same thing as saying to you write the equation of the tangent line. Or if they say use this, find the linear approximation, same thing. Okay, all of those things are just saying write the equation of the tangent line. So that's going to be y minus the y value So we need to plug in 9. So square root of 9 is 3. So the y value is 3 equals the slope times x minus the x, which is 9. The last thing you should write, if we are doing it, linearizing it, we're going to use it to estimate, is do go ahead and move that. Now, remember, some of you can just always write your equations directly like this. That's fine. Just don't ever distribute unless you need to later. Later you can distribute. Don't ever do it now. Okay. C says, using your result from B, estimate the square root of 9.1 with no calculator. Okay. So basically, f of 9.1, so we don't know what f of 9.1 is, we're estimating it by using what we found. So it is approximately equal to y of 9.1, because we called that equation y, okay, that linear approximation. So that means we plug in 9.1. So the equation was 1/6 times 9.1 minus 9 plus 3. That was the equation. We're plugging it in. Well, I don't have a calculator, so I need to either know what the 1/6 is as a decimal, or I can just use a fraction for inside. So since I don't have room, again, this is what you should always be doing. Just arrow up here. We're going to continue on. So this equals 1/6 times 1/10 plus 3, which is 1/60th plus 3. 3 and 60th would be 180 60ths. So this is 181 out of 60. I'm going to tell you that that's approximately 3.0166. So if we had known that 1/6 was 0.16 repeating, 666 repeating, we could have just used that decimal, but I'm going to just write it that way for your information. Okay, now what we want to do is graph the square root of x on this graph, and then put the tangent line at x equals 9. So to graph a function, if you don't, you always plot some points. We should know roughly what square root of x looks like. We know that we have a point at 0, 0. We know that if x is 1, y is 1. The next good point to check would be when x is 4, y would be 2. When x is 9, y would be 3. When x is 16, y would be 4. Because we want to plug in numbers that make sense. And then we connect that with a smooth curve. And that's the graph of the square root of x. Now we want to draw a tangent line at 9. So I'm going to use my ruler again. You can grab your protractor. And I'm going to lay the ruler at 9 and try to draw the best that I can, which is this point right here. So I'm going to tip it and get as close as I can get. Now we're hand drawing all this, so obviously, you know, we're doing the best we can here. It may not be too perfect. That's okay. So I'm going to draw my tangent line right there. Now you will notice how close the tangent line is to the graph. It's really close, as long as I'm by 9. Now if I were to keep drawing that line, okay, so if I went back up here and drew it further so that you can see why it doesn't work later, if I were to keep drawing that line, okay, out, you can see that it's a good approximator close to 9 for sure. So around here, it's a good approximation. The tangent line is really close to the function. But over here, if I tried to use the tangent line to approximate the square root of 2, that wouldn't be a very good answer because it's pretty far away and the tangent line isn't that close to the function. So that's the idea about a local approximation. We want to be close, okay? Then I want you to look, and where is the tangent line? Well, the square root of x is concave down everywhere, so, and you can see the tangent line is above. So then the question is, The E says, explain why your answer is an overestimate or an underestimate. Which is it? Well, it's going to be, my estimate is going to be an overestimate. Okay, so f of x is concave down. So the estimate is an over approximation because the tangent line lies above the function. This is an actual AP question asked all the time on free response. Is your estimate an over or under approximation? And this is the exact reason you would give. It's an over approximation because the tangent line, because the curve is concave down. So therefore the tangent line lies above the function. So this is going to continue. This will come up quite a bit because it's definitely on the AP test. I mean, almost every year there's a free response question, and one portion of it you have to do an approximation, and you have to give that thing. So the actual value, if you do this square root of 9.1 in the calculator, you're going to find that the square root of 9.1 is approximately 3.0166. And I'm going to do that in the calculator real quick, but you can do it in yours. So I'm just going to add a calculator page and do the square root of 9.1. And I just have to hit enter. It'll give me approximate because I have a decimal in there. So our approximation was super close using the tangent line to the actual real value. The next question says, would this be good to use for the square root of 25? So that's estimating at 5. And again, the answer would be, no, this would not be as good of an approximation. Now my lines are big and fat, so my tangent line doesn't look too far away, but it's definitely farther away at 5, okay, than it is, oh, and they actually asked for square root of 25. So never mind, not even 5, square root of 25. So 25 would be way over there. So your graph would still be coming down like this and your tangent line would be going up. So definitely at 25, this would not be a good approximation. It's too far away. Okay, so that's all you have to say there is it would not be very accurate. So this would be no. Square root of 25 is too far away from the point of tangency. And what you could say is it is outside the neighborhood. So in other words, it's outside of the area where the linear approximation is good. Okay, so it's only good in a little local neighborhood, and it's too far away. All right, so let's look at this question. So again, this is the tangent line approximation. You could also write, if they ask you to do a linear approximation, it means draw the tangent line. They could say to do the local linearization. All of those things basically just say do the tangent line at that point that you're near, at a good point, so a point where you can answer the question, and then use the tangent line to approximate the function a little bit away. Okay, so we're going to do the rest of this in class. We have a lot of drawing things to do, so we're going to kind of draw those together. Well, the rest of these that we have to draw on. We're actually going to do the last example, which is derivatives from a table, and we're going to kind of look at that. But we're going to do the rest of these drawing ones and stuff together. And so you just need to go to the last page on the very back where it says derivatives from a table. All right, so this is you have a 100, well, I'm going to go with a 99% chance that you will have a question on the AP test that is what we call a table question. Okay, so you will see this on the AP test, unless there's just a weird thing that happens, okay? And one of the things that we're going to do right now is one of the things they can ask you to do for that particular type of question, okay? So you're going to use this table of values to find the derivative at a different place. Well, I can't actually find the derivative because derivative is instantaneous rate of change. But the best estimate for instantaneous rate of change is the average rate of change close to it, okay? So what we're going to do is we're going to estimate all these by picking numbers that are close. So let's start with -2. We're going to estimate the derivative at -2. Well, to estimate the derivative at -2, I'm going to pick the two closest places, and I'm going to use these 2 points, and I'm going to write out the derivative. Very simple. So what I'm going to do is say f prime of -2 is approximately. Be sure you're practicing notation, notation, notation. This is not what it equals. This is approximately what it is. So we're going to take the y value minus the one other y value over the corresponding x minus a -1, so that'll be +1 plus x. And that's going to be -10/3. Or +10/3, sorry, -10 over -3, so you get +10/3. Then the question says, what's the behavior of the function at a? Well, if you look at -2, well, you go from -6 to 2 to 4, so it appears to be increasing. And that is what we're going to write. So the behavior is that it is increasing right there. Okay, so it is increasing. And my justification is because the derivative at 2 is positive. That's actually going to be my reason. If the derivative is positive, the function is increasing. Okay, and you can see that when we look back at the graphs. So let's go ahead and do a couple more of these, and then I'll leave some of these for you to do. So again, f prime at -1 is approximately. So back at the table, if I want to estimate what's going on at -1, I'm going to pick the 2 points that are closest around it, and I'm going to find the slope. Okay, so I'm just going to take again the y minus the y. So you're going to use 2 minus -1. Just get in the habit, as soon as you say minus -1, you write plus. That's another one you're going to use it so much. It's better for you to get in that habit. And the bottom is -2 minus 0, so we get -3/2. Well, a slope that is negative tells me the function is decreasing. So f prime of 1 is less than 0. That's my justification for that, and that's what we're going to say. And actually that's at that point. So at -2, 2, and this is at the point -1, 4, because the function's not negative, but at that point, the derivative appears to be negative. Okay, so let's do what happens at 0. So if we're going to do 0, again, we're going to pick points. The best estimate that we have for the instantaneous rate of change is the average rate of change around it. So the average rate of change here, you're going to have 4 minus 4 over 2 minus -1. So again, f prime of 0 is approximately, not equal, but it's approximately y minus y, which is 4 minus 4, and then it doesn't make any difference which way you do the bottom. You can do 2 minus -1, which is 2 plus 1. Whatever you do, it doesn't matter. You're going to get 0. So if the slope is 0, we say the behavior at that graph is that it is constant. So since f prime of 0 is 0, we're going to have also a relative extrema. We'll talk about that later. So I'm going to let you do the last two. So I want you to do x equals 2 and x equals 3. So I hope you're listening to the video. I want you to fill those in yourself. And then we'll look at them in class. So make sure you do them to see if you're doing it right. And so important facts and findings: if the derivative is less than 0, then the function is decreasing. If the derivative is greater than 0, then the function is increasing. If the derivative equals 0, then what's going to happen is you could have a relative maximum if the derivative is 0 and the graph changes from positive to negative, or the function changes from, the derivative changes from positive to negative. And the reason is because a positive derivative means increasing, negative means decreasing, therefore that must be a relative max. Okay? And then a relative minimum occurs when this is 0, and then the opposite, it changes, the derivative changes from negative to positive. So we will finish that in class, go through this a little bit more, but that gives you some things to think about. Be sure you finish the last 2 parts of the table, and then we will go through this again in class.